work I'm doing together with Riviera in Vienna and Joyce in Brussels, and of course the rest of the gymnastic. We've seen a lot of asymmetrical PLanetary today, and I'll make this quick. There are a lot of asymmetries. Also before, in the post-AGB phase, we had a lot of asymmetries. But people generally think the AGB wind is just vertically expanding into eternity. But actually we know that we have three interaction cases. The most prominent one is the interaction with the ISM. So when the AGB star is moving faster, let's say about 30 kilometers per second, you get a shock in the phase where the ISM and the wind are balanced, and this is called a bow shock. And the bow shock is actually defined only by the standard distance R0, and this depends on the mass loss, wind velocity, the velocity of the star, and ISM density. And the observations that we make are mainly defined for it, and extremely rare cases are also found in UV, and one of these is IC 10^16. This is a galaxy image by Antonopoulos. As you see, it has this very typical wind shape. It's a fast-moving star. The other interaction case we find are two winds that are interacting, and this happens in the late stage of the AGB. So when you have a young, fast wind that sweeps up the old, regular AGB wind, and this occurs during the thermal pulse. And this is what we call a detached shell object, and all of them are carbon stars, and it can be traced in CO and dust and on scattered light. An example is here TT Cygni. You see it here in CO, and this one is the dust. It's a clumpy thin shell, and the width is only 2.5 seconds. And this is a dynamical age of this shell of only 500 years. The last very prominent example is the interaction of the wind with the companion. And I'm talking here only of wide binary systems. And what happens here is that the primary moves around the center of mass, and there's a mass transform in the companion, and this creates a supersonic orbital motion, and the remaining AGB wind then pushes out this accretion wave, and we have a spiral. I think Young Kim and Shazrin Mohammed will talk about this extensively tomorrow, so I'll make it short. It is still the first, and it's still the best known example for this AFGL 3068. It is HST scattered light, and you see 5 windings with a diameter of 25 arc seconds. And with this separation of the windings, you can actually get then the orbital period of the companion and the separation of the companion. And the author didn't know that this is a binary star back then, and proposed that it's 120 AU away from the primary. It was later confirmed that it's actually really 109 AU, so it's quite a good prediction. What I show you today are Herschel images, so we used Herschel pucks and imaging at 1760 microns with resolution of 1 arc seconds, 70 and 2 arc seconds per pixel in 1960s. All objects I show are from the mass sample, so it includes 78 objects which are mainly AGB stars, and there are also a few supernova remnants and other trees. And we found that 60% of the 78 objects are extended, and 70% of these extended envelopes are asymmetric. And you raise the number on large scales from 5 objects to 33. And the rest, the 30%, are just the rings or detached shells, which are spherical symmetric. We also have 18 out of 78 objects are binary stars, and 10 of these have extended envelopes. And you can put them in these interaction cases. You have 5 out of 24 Bohr-shock objects are binary stars, you find them here. Interestingly, only 1 out of 13 show this kind of win-win interaction with RSL. It could be that if you have a binary star, it would just destroy this spherical symmetry, so that we only have 1 object here. We have the so-called eyes, which have this lemon eye shape, and we have no clue what shapes them, and we find that 2 out of 7 of these eyes are binary stars. And we have the regular case, so this might be binary interaction, like spirals and other stuff we see. And these are 4 out of 7 objects are binary stars. And one very prominent example is Myra. You might have seen that before. This is a galaxy UV image from Martin. fast Riviera center, I think over 100 kilometers per second. They found this strong bow shock in the UV and this 2-degree long tail. And if you go to the X-ray, you see the binary system with the white dwarf and the UV star minor, and it's also some kind of mass transfer. The orbit of this system is really quite unknown. It's at least 800 years, but it could easily be doubled. What we see in the far infrared, if you see this at first sight, you say, okay, this is just the same as in the UV, it's a bow shock object, but that's not the case because the bow shock is somewhere around here. What we actually see is the freely expanding wind and the so-called astrosphere. And if you have a close look and you see it actually better in this intensity cut, you have 4 kind of arcs around the star. So it's A, B, C, and close to E. And if you're very optimistic, you also see kind of E here. And this might reflect the spiral. And Shazri Mohammed in that time did XPH simulations for Mara with Mara configuration to find a nice spiral pattern. I think she'll talk about this tomorrow. And we just asked her to let the spiral freely expand, but put it in kind of a bow cone. And she came up with this really nice model, and I think this could reflect Mara very well. What we're now working on is Pi-1 is a very complicated case. It's a very old AGB star, so relative of the AGB. It has a known main sequence companion, but it's a quite wide system. You see it's 450 AU, and the period is over 6,000 years. But if you have a look at the delta mu, so this means you have a difference in the proper motion between the short-term Parker's proper motion and the long-term Tycho 2. And if you also look at the Parker's intermediate astronomical data, you see that the focus center actually does this kind of orbit. And this only happens if the star is, if you have a companion that is separated by, let's say, 4 to 30 AU, and the period must be 10 years. So there's no way that this known main sequence companion, which has over 6,000 years, produces this movement. So it could be that Pi-1 is a triple system. If you go to the far infrared, you see the elliptical CSE. This is nothing new. It was already observed in the CO earlier. But the interesting fact is this kind of arc you see in the east. And as a very optimistic person, I would just say, yes, it's a spiral. But then you have 2 possibilities. One is that the close companion shapes this. But then the spiral separation would just be 0.2 arcseconds, so it's much smaller than 1 pixel of this image. But it's clearly impossible. So then we tried if the main sequence companion with the parameters CRP could produce it, and we fitted the spiral through. But actually you can fit a spiral through everything if you just have like a small enough part of the spiral. But what is a good constraint is that the starting point of the spiral must be actually the location of the companion. And we're not so far away from that. And if you just assume that the orbit is a bit inclined, you just get it. And my last object I want to show is RF. It's a well-known symbiotic system, separated by 12 AU. And in the optical you see this nice ring. It was first found by Sullivan Group, I think 30 years ago. And this is actually associated with the Nova outburst some 100 years ago. So this is like also found in Korean history books. And if you zoom in into this central part, you see these kind of 2 jets with a curved trajectory here to the south. And it's a quite huge structure, it's 5,500 AU. In the far infrared, we just see a counterpart of the optical ring, but not completely. You only see here the northern part, here the southern part. And we have no clue why we don't see this kind of bridge, because this is definitely as strong as the southern one. And if you have a look at the temperature map of the object, you see here a temperature gradient. You see that this point is, I think, about 8 Kelvin warmer than this one up here. So the structure could actually not be circular. This wouldn't make any sense. And so we went to our atmospheric modeling group in Vienna and asked them if they could model the SED. And they came up with a temperature model of the wind. So you see it's gradient is quite constant. So this is reliable above 500 AU, and we are clearly here much further away than 500 AU. And we could take these temperature predictions to actually do a deep protection of the arm, and we find that it's inclined by 77 degrees, which is quite close to the inclination of 72 degrees of the outer plane. So I conclude here that many stellar AGB winds are asymmetric, on large scale of course, and the presence of companion alters the wind morphology and either have a spiral arc and or bipolar outflow. But also multiple morphologies are possible. So you could have, let's say, a detailed shell inside a bow but you could have a spiral inside a bow. Interestingly, the ring morphology lacks binaries. We only have 1 out of 13 objects, ring objects, in the binary system. So the question here, does the companion destroy this spherical symmetry? And only 3 out of 10 objects show no binary interaction signs. So these we don't see anything that we can relate to binarity. And for the future, there will be arm observations for Palma-Blue, City and our quarry, and we hear more about that from Riviera tomorrow. Thank you.
Okay, last question for today. Somebody, please. I will pick somebody here. You don't want it to happen. Question. Okay, Christoph, do you have an announcement? Okay. So.
Somebody is taking